design of a low-cost weather station for use in sensor network systems for agriculture and engineering education. A case study realized by Matheus de Souza Marins and others in Centro Federal de Educação Tecnológica de Minas Gerais, Leopoldina, Brazil. This presentation is subdivided in a brief introduction and background, followed by the purpose of the work and the method used to do it, the results, the conclusions we may draw from it, and the references in the end. The project presented here is an interdisciplinary approach made in a control and automation engineering course. In agriculture, knowledge about meteorological and climatic variables is essential for taking action in various activities. It may be the difference between their success and their failure. However, often due to cost, the density of weather stations is low in several regions, causing great uncertainty in the models of climate estimates. The need for an affordable solution to this and a considerable number of sensors and integrated technology that can be used in engineering classes motivated the construction of a functional weather station with the meteorological analysis of its sensors. The schematic diagram in this figure represents its parts. The sensors collect data from the environment, and then a microcontroller processes them and moves them forward to a Wi-Fi module. From there, the module sends the data to the cloud through an MQTT protocol. The development of its parts was approached in different subjects of the course. The sensors analysis were developed in metrology classes, and the microcontroller and Wi-Fi communication part was approached in programming and computer networks classes, respectively. 7 sensors were chosen to be part of the weather station: anemometer, windsock, thermometer, rain gauge, hygrometer, radiometer, and the gas sensor. To investigate their reliability and create their error curve, the student t-statistic distribution was used, and the students in class calculated meteorological variables such as repeatability, random error, tendency, and systematic error. For the sensor's calibration process, climatic conditions were simulated. The anemometer, for example, was set in 12 different positions in relation to a static fan. For each position, 30 measures were taken. This data was analyzed and compared to another superior meteorological characteristics device. The intensity levels of the investigated variables sought to match with the already known classifications. For the wind speed, the Beaufort scale was used. For the rain rate, this one, for example. The rain intensity changes according to the flow. A light rain corresponds to a flow of less than 5 mm per hour, a moderate one between 5.1 and 25 mm per hour, a heavy one between 25.1 and 50 mm, and a very strong rain is over 50 mm per hour. Based on this, our analysis describes for which level in question the sensors have a good meteorological behavior. The rain gauge works as desired under light and moderate rains. When the intensity goes beyond that, the random error of the measure increases, so no one can know when it is reliable. After that, the apparatus for the sensors, microcontroller, and Wi-Fi module communication was developed, as the embedded software is required to process and send data to the cloud. By the time of this presentation, the weather station must be already installed, and the climatic variables monitoring can be accessed in real time by the link or the QR code here. So it is possible to conclude that there are valid calibration values to 29 degrees of freedom and 95% measurement certainty criterion, as well as this project allowed the students to have a multidisciplinary integration of skills. So here are my references, and I would like to thank you all, especially Cefet, FAPEMIG, PET, and ICA Edu for the opportunity. Bye.